Um, Hello, my name is Ellery Smith, and now I'm going to present a natural language to natural language system for data exploration using graph databases. First, I'm going to play a demonstration video showing the system in action. We now give a demonstration of our natural language to natural language data exploration interface using a semantic graph database as an intermediary. To begin with, we will show a demonstration of this system in action. We utilize the use case of the PubMed Biomedical Research Database. From this database, we have collated a corpus of research paper abstracts and fed them into our system to build a semantic graph database. For this example, we use a subset of a few hundred related abstracts concerning oncogenetics. We can query this database using natural language, as we will now demonstrate. Firstly, we can obtain some basic information about the data, such as how many occurrences of genes have been detected in the text and added to the database, or how many different diseases were found. We can similarly check how many unique genes are stored in our knowledge graph. And we can list them using a query like the following. Now, we demonstrate some more informative queries. For example, we can ask which gene expressions are associated with pancreatic cancer, according to the literature in our database. With this query, we can see the results formatted in the style of a relational triple, where a subject and object are connected by a semantic relation. The two gene expressions are shown on the left as subjects, with the relations demonstrating an association with pancreatic cancer, along with some contextual information. For example here, invasive depth of pancreatic cancer. This reflects how information is stored in our knowledge graph, as semantic triples which we extract from natural language text and form into an ontology. If the user requests relationships between concepts in a query, we can present a user with a more precise and structured knowledge representation than traditional search methods, and allow database-like search without the need for a precise design. In addition to the triple, we provide a link to the PubMed abstract where the result was obtained from, to allow the user to view additional context and verify the validity or research importance of the results using their own domain knowledge. We intend to integrate this system into the overall inode dashboard in the future, which will provide this contextual information directly alongside the results. We can additionally try queries such as which gene mutations were associated with colorectal cancer, find out which genes may be overexpressed in breast tumors, or increase brain metastasis. All the results returned here are shown in real time, and the response time for our system is fast enough to allow for an interactive data exploration experience. There are also possibilities for more general queries, such as what protein deregulation might be associated with, or what gene expression can correlate with. We will now demonstrate the process of constructing a sample database using a small subset of abstracts. One component of constructing the database is a set of domain ontologies, which consist of a hierarchy of labels, with each annotated by entities. We show here the disease portion of the input ontology, which contains a list of entities and synonyms for these entities. For biomedical data and many other domains, these ontologies are widely available, and it is simple to output them in the required format. Thus, it will be relatively simple for a variety of textual domains to be integrated into the system with minimal input from a developer with domain knowledge. We will provide an API and instructions for this process with the full inode release. The other component is the textual input, which can be supplied in plain natural language text. Here we show the input abstracts for this demonstration, which represent the abstract text from a small number of papers. With this, we can use our knowledge graph generator to build a database. Each paper takes approximately 1 second to be analyzed and inserted into the knowledge graph on a medium-powered laptop. As we can see, the tool found 329 relational triples in the text and built them into a knowledge graph. To show that this process worked, we opened the interactive query tool and asked which diseases are associated with increased cancer risk. The results show that the database was built successfully. Okay, so now that you've seen the system in action, I'm just going to talk a bit more about the details and the implementation. First of all, overall, what the system offers is a fully end-to-end natural language to natural language interactive search interface. The way that it does this is by building a semantic representation of knowledge from natural language text, constructs a graph database from this, and uses this as an intermediary representation. Because of the way it's been designed, it can be run on any text domain potentially, or any given use case. As I've shown in the demonstration, you can build the ontologies yourself using the existing ontologies and construct a custom database using a natural language corpus of text. It has rapid query interpretation, as was shown in the demonstration, so you can do a query interactively. And under the hood, it uses some novel linguistic algorithms for processing the queries and constructing the ontologies. The advantages of this type of search over existing methods such as information retrieval or relational database methods is that versus information retrieval, you can have a semantic and a syntactic understanding of the text, which gives greater precision. And it also supports aggregate queries, as I showed in a demonstration such as counting or grouping nodes together. And versus a relational database, you don't actually need to go through the process of designing a schema or a database, and it can handle messy textual data automatically. In the previous presentation, we were shown a graph database using using RDF and SparkQL. However, here we use Neo4j label property graphs and the Cypher query language. The graphs look like what is shown on the right here. And we use these label property graphs as a more natural representation of natural language text versus the traditional RDF triple store. And we choose the Cypher query language because it represents a more smoother transition from natural language input to the query language itself. It also has other advantages in the way the database is constructed. As you can see on the right, we have one of the nodes from the graph database, which is the HPV virus node. And you can see that in the properties, it has 5 different labels, which we use for searching, and it can be marked as a disease, virus, syndrome, diagnostic procedure, pharmacological substance. And this is not easily done in an RDF database, but it's much easier in a labeled property graph. And we also have descriptors and contextual terms associated with each node. These are much simpler and compact to represent and flow more naturally from a natural language sentence into a database. And additionally, relations also have a similar multi-label system and hierarchical relations, which allow for much easier searching and just general better model of text data. The way that the overall system worked, as I showed in the second half of the demonstration, is that the ontologies, which are constructed in a simple JSON format, are fed into the system, and these automatically construct the schema of the database. And then the triple extractor system finds subject, predicate, object relations from the input text corpus. The next step in the pipeline is an entity linker, which uses the schema and the triples, matches the information together, and then constructs the knowledge graph using this. When you are querying the database, the natural language queries are translated into the Cypher graph query language and executed. The triple extractor portion of the system is state-of-the-art in the current benchmarks. So the extracted knowledge should have a high precision. And the entity linker and the triple extractor, in addition to being high quality, also provide additional information because of the linguistic algorithms used. As was shown in the annotated node slide, you can add contextual information or descriptors or other forms of contextual data from the natural language triple using the linguistic methods to extract them. And the query interpretation is done using some kind of similar linguistic. Technical details are available if you require them. In the future, we plan to test the system on other domains, such as Wikidata, which is Wikipedia plus a semantic ontology. And if we can get this system running, we can potentially verify if it is truly generic and adaptable to other data sets. The next step would be to integrate into the inode dashboard and provide the information that was shown in the demonstration in a much cleaner UI and more readily accessible context. And we can also implement more complex queries than was shown in the demonstration and potentially have some result ranking and quality metrics attached to the results for a better user experience. Thank you for listening.